Hello students, I'm Mr. Morgan and we're going to look at graphing distance and time. The first physics scenario that we're going to look at is how distance, time, and velocity relate to each other. Remember, distance and time are fundamental variables, and velocity is a result of a relationship between distance and time. In order to look at this relationship, we're going to have to start with a graph of some data, and we're going to look for trends in the data on the graph, which just means we're going to draw lines of best fit where appropriate, and then we're going to use those lines to build equations that will help us make meaning of our observations. So imagine you've gone and collected some data and you need to put it in a graph. So we need to come up with some parameters for creating a proper graph so that we can look for trends. The first rule is that time in physics is going to be almost always on the x-axis. It's going to be our independent variable. Don't forget to write down the units you recorded time in. For the purposes of this graph, we use seconds. Distance is going to be the dependent variable, and it's going to go on the y-axis. Then you need to decide on a range that is just larger than your data set. Remember, if you make the range too big, you won't be able to see the trends, so try to make it just a tiny bit larger than the data that you recorded. Next thing you're going to do is plot your data points. And finally, you're going to draw the simplest best fit line or curve that matches the data. You may have multiple best fit lines in your data, and that's okay if you have distinct intervals. We can have different slopes recorded on there. So what are some graph features that can give us some interesting or useful information about the data we recorded? The lines of best fit have direction, and that can tell us about whether we were moving forward or backwards, that slant up or down. We have steepness of each line, so that gives us an idea of the speed we were traveling. We have the length of each line segment. That tells us about how long we moved in that direction, sort of the change in time during that segment. And finally, we have the x and y intercepts, and we can obtain information about what it means to cross the x and y axis for the data that we collected. So here is a new graph for the purposes of illustrating the direction of best fit line and what that means for our information, how we interpret it. So here's a graph of a purple car, a blue car, and a green car. And as you can see, the blue car has a downward direction slope, the purple car has an upward direction slope, and the green car has a neutral or flat direction slope. Well, what does this direction mean? It means that the blue car is moving backwards, it's losing distance over time. The purple car is moving forward, it's gaining distance over time, and the green car has actually stopped. The next bit of information we can gather about that best fit line slope is the speed at which the car is moving. The steeper the slope on this graph, the faster the car is going. So a very steep slope is fast, a medium slope is medium, and a slow slope is a shallow slope, and a flat slope, of course, is stopped. The next trend that we're going to interpret is the length or duration of the best fit line. The length of that line tells us how long the interval of motion is. So we can see that the green car is standing still for 2 minutes, the purple car is moving forward for 6 minutes, and the blue car is moving backwards for 4 minutes. Intercepts. What do the y and x intercepts tell us about the motion of the car? For this graph, I have a blue car and a purple car, and the y-intercepts, as you can see, it starts at 0 and counts up to 5 and down to -5. Well, that 0 is a point of origin or a point of reference for motion that I've chosen. we can see that the purple car starts at my point of origin, and the blue car starts 4 kilometers away from my point of origin. The x-axis, or the time axis, tells us at what time the cars pass my point of origin. So the purple car actually starts at my point of origin and moves away, and the blue car passes my point of origin at around 2 minutes. In summary, make sure you're looking at best fit lines, or the curves, and not the actual data points when you're trying to build your equations to explain your data. You can also learn something from the direction, size, and slope of the intercept for each line, and that will tell you something about the motion of the object. So with that in mind, let's try our essential question out. What would a graph of an object going backwards and slowing down look like compared to an object speeding up and going forward?